All right. So, hey everyone, and welcome to today's Vinn Explore event, where we're going to listen to the eminent Carl Lindberg talking about AI. For you who haven't been here before, and I know there was at least one person I spoke to earlier that haven't been here before, you are now in the great building of Vinn Group. You might wonder who is Vinn Group. We are a company that's been around for 10 years. We have a fairly simple business model. We start great world-class consultancy agencies. We've done that for 10 years. We started 18. We sold a few, and today we are 12 great companies in the group, whereof 10 sits in this house and 2 sits in Stockholm. And then all these great consultancy companies service the great companies in Sweden with brilliant consultancy services in many areas, such as brand strategies and innovation services and software development, etc., etc. So my name is Pierre Renholt. I'm the CEO of Vinn Group. And I'm not going to talk more than that. I just want to hand over to Carl Lindberg. So let's give him a great applaud and welcome.
Hi, it's great to be here. Like I was introduced, my name is Carl Lindberg. I work at Senuri now, work there to build the new AI center, which is a national effort to bring together AI resources. I also am a co-founder of Sigma Stocks and have a background in entrepreneurship. And also a professor of math from time to time. I thought I'd start this lecture by telling you guys about a good friend of mine, Reine, his first summer job. This is 25 years ago. Reine was 15 at the time. It was his first and, as it turned out, only summer job. He was supposed to come in at the local logistics company, and during the summer he was to replace 2 women who had that job during the rest of the year. And his job was to compare 2 lists of incoming and outgoing shipments. And they thought, since this was going to be in the summer, that he could probably do that just one person, do two persons' job for one person. But to compare 2 lists for a soon-to-be engineer like Reine, that's not something you do manually. So he spent his first day of the summer job to write a script which made the 2 women superfluous. They had no job when they came back in August. And the rest of the summer, he designed and constructed a Japanese garden outside of the logistics company. And I think this story of the 2 unemployed women coming back from summer vacation, not having a job anymore, kind of nicely summarizes the threats and promises of digitalization and AI. And speaking about digitalization, right, and AI, that's almost semi-mandatory when you give talks about AI to have a picture like this at some point, right? Because it's kind of what people tend to think about when they hear AI and competent AI and stuff. But what we're actually should be afraid of is not so much Arnold Schwarzenegger coming in and killing us. We shouldn't be afraid of vicious machines, but rather of machines turning competent to do things that competent machine and things going bad out of accident, essentially. Because it's not entirely easy to foresee every aspect of a design, to see the entire picture. This is a picture of a famous one from, it's the Tacoma Bridge in the US, or used to be at least. What they had, I mean, there weren't stupid people building that bridge, right? But for some reason they missed out on that the natural frequencies of that bridge were the same as those induced by the wind. You know, natural frequencies essentially. The only time in engineering you want a self-reinforcing pattern is if like push your child and sling, right? Swing. You push and the child comes back and you push it, right? In every other aspect of engineering, you don't want self-reinforcing patterns, right? So this is what happens, and that bridge collapsed like 2 days after, or something like that. So it's hard to foresee what's going to happen in the system. in terms of AI, a modern thought experiment put forth by Swedish-born Nick Bostrom, something called the Paperclip Armageddon. And it's essentially that the point of that story is that if you give a competent AI a goal of producing something which might seem benign, in this case, you give a competent AI the task of producing as many paperclips as possible. Right? This seems pretty harmless, but as Nick then said, that suppose we have an AI whose only goal is to make as many paperclips as possible. The AI will realize quickly that it would be much better if there were no humans, because humans might decide to switch it off. Because if humans do so, there will be fewer paperclips. Also, human bodies contain a lot of atoms that could equally well be made into paperclips. The future that AI would be trying to gear towards would be one in where there were a lot of paperclips, not so many humans, right? And this illustrates an important point, that it's not entirely easy to design. Systems will behave like you design them to behave, but it's not entirely obvious what you have designed them for, right? And even though this particular example most likely won't happen, it's just meant to illustrate the broad problem of managing powerful systems where these systems lack human values, right? And even if the Terminator scenario does not come true, which probably doesn't, we still have a lot of problems, because before AI turns competent in general, right, it's going to be competent in a lot of different sub-areas. So that is, before you have a system which can do everything better than us, it will be better at each thing that we do. And computers are already better at a lot of things, like playing chess and stuff like that. And this gives us tremendous problems, if nothing else, that we're at risk of enormous social problems. Because for the first time in world history, large parts of the working force can totally lack economic value. We can't even turn prostitutes, right? Because they will do that better too. Okay? So that's a serious issue, right? And the only hope we can really have in this process is that it will be slow enough so that we have time to adapt. During the Industrial Revolution, things happen more slowly, right? But now it's these tensions, the social tensions, could present themselves faster this time around. And why is the slow pace good for us? Well, if we have time to adapt, we'll come up probably with new things to do. And on a more optimistic note, there were a few yoga instructors and bloggers 200 years ago. Yeah. So which jobs are more at risk than others? Well, I wouldn't tell my children to be a driver of some sort, taxi driver or a truck driver. I wouldn't tell them to be pharmacists. Doctor, maybe. Factory worker, absolutely not. Right. Nurse, teacher, software engineer, they're probably safer for a longer time. So just to illustrate a few local examples from how these threats can come about. Vinn, a local accountancy firm, digitalizing accountancy essentially. Threats to lawyers. Ross is an AI which helps writing agreements, right? A lot of what people pay lawyers to do are things that are, in the modern world, easily digitalized. Sigma Stocks, a local company which I founded, a short disclaimer, want to help people invest in stocks instead of expensive and inflexible mutual funds. Threat to the financial industry. So there are a lot of reasons to worry and think about AI, but what I want to do now is to come back to the question what it is in the first place, and some of its history and what we can do today. So the whole field started with Alan Turing, and the natural question, can machines think, right? That issue has been around, and philosophers have thought about that since Descartes, right? But even the definition of thinking and machine are not entirely clear. Turing, by the way, this is not the only field he found. He's just an amazing mathematician, and probably the most ungratefully treated person in the history of humanity, right? He pretty much, if you're going to name one person who won the World War II for us, it's him, right? Where he cracked the Enigma code, which essentially won the Battle of Britain. And because of him being homosexual, they chemically castrated him. So it's you think they would have forgiven that, given that he shortened the war by like probably 20 million people in 2 years. So anyway, Turing suggested a test called the Turing test, where an interrogator converses with a man and a machine via text-based channel. If the interrogator fails to guess which one is the machine and which is the man, the machine is said to have passed the Turing test. So you get to ask questions to someone you can't see, like tell me a joke about politicians, so I'm not just as funny, but can you add 79,536 to 46,960? Then the machine pauses for 30 seconds. I know the answer, I'm not going to tell you for another 40 seconds. And then tells them the answer. And although the Turing test is not without flaws, I mean, it doesn't capture visual or physical abilities. Its beauty is in its simplicity and objectivity. It's only a test of behavior, so not of the internals of the machine, so it doesn't really matter if you do things with neural networks or logical methods or whatever. And to be able to pass the Turing test, the machine must be able to communicate with language, represent knowledge, reason, and learn things from data, machine learning, essentially. And ideally, you want to pass something called the total Turing test, where you also put in vision and robotics. Kind of like you should be able to hand, through the hatchet, you should be able to hand them like a Rubik's Cube or something like that. Or ask questions, or what is it that you see on a screen. And these six disciplines constitute most of AI. In the recent day, machine learning has come to dominate the area. In particular, deep learning, which we'll get back to. But in terms of intelligence, perhaps imitating machines is the wrong metric here. It's true that humans possess abilities that language, vision, motor control that are currently better than the best machines. But on the other hand, machines clearly have characteristics that are better than us. They're a lot better at speed and memory, so it's not obvious why we should settle for human level performance. It's also not certain that the solution to building an intelligent machine is to imitating us, right? Because we know how to build airplanes like birds fly, but we just choose not to do it. And on an optimistic note, I thought I'd show you the state of the art between human football players and robot equivalents. So they have some way to go, right? So instead of asking what AI is, let's turn to a more pragmatic question of what AI can do. So I'll go through some examples where AI has been successful. And some of these examples are ones that AI is already widely deployed in practice, while others are fun but not necessarily practically useful. So in 2014, Facebook research published a paper describing their deep face identification system, which essentially means that you can put a picture up on Facebook and the algorithm will actually tell which person's around there. These things are quite successful these days. See, their system is quite fast at recognizing people, right? So this, I think, is from a Tom Cruise movie somewhere. On the other hand, it's not flawless. So as Tom Cruise was escaping his car, he flashed a remote at him, urging him to stop, right? And this comes back time and again in, we'll come back to it later during this talk too, that while the machines can do incredibly impressive things, they're still in some sense just still not smarter than just a bike, right? I mean, they can do things, but it's not like it's understood what it's doing. It's more an algorithm. Areas where machines are quite good, machine translation, started in the 60s, where the US government for some reason was keen on translating English into Russian into English. Now in Google Translate supports like 90 languages and has 200 million users today, so it's exceptionally successful. And you kind of know that if you're watching some crappy movie on Tuesday night on Channel 9, you can be pretty sure that Google Translate was involved in the translation of it, and maybe not even a human at all, right? Speech recognition, which is like your Sears and stuff, which I should also point out that this is something completely different to understanding. It's still just, I mean, it doesn't understand what it's hearing. It's just that it can take your order. It can know in some sense that you want to order pizza, but it can't really, doesn't have a concept of what pizza is, right? So after these success stories, in some sense, we should discuss some technologies which are promising but not quite ready for the prime time. This self-driving, autonomous driving, like Synuda, where I work, it's had some early successes, semi-successes with some Google car in 2005, managing to drive some 132-mile off-road course. But it's a few years ago, these self-driving car companies were quite cocky. So they thought they were real close to managing to construct cars like that. But now they're considerably more humble. I thought I'd show some sharp research from Synuda on how this car up in upper left is supposed to pass an intersection. And first of all, every time it changes color, it changes the decision to drive and brake and whatever. And first of all, the first time it doesn't know anything, it just drives. And after some 40,000 episodes of training, it is learned to wait, essentially. Yeah. But again, there's no understanding, and that's the frustrating part about doing these things. It's no understanding in it. I mean, you can train a car to brake at an Audi, a Opel, a Fiat, a Mercedes, brake at anything that counts on a road. But if you throw a baby out on a highway, it'll probably run it over, which is, from a practical perspective, not ideal, as most of you realize. So natural language, reading comprehension, is still regarded as an unsolved problem. So one of the specific incarnations is the task of reading comprehension, where given a passage, your goal is to answer a question about that passage. Here you approach understanding in some sense. So one of the most popular recent data sets for reading comprehension is something called SQUAD, which is a Stanford data sets with 100,000 questions coming from Wikipedia. And the machines can do quite well on these understanding things. But like anyone who's ever corrected an exam in like high school or university, everyone who's done that has had to approve a student who you kind of know hasn't understood anything, right? And this is kind of the same thing here. If you ask more probing questions, you realize that these systems, while they get the right answer, they still haven't really understood it, right? And one particular hot topic in computer vision now is generating images from words, right? I have trouble seeing this. I'm going to stick to the screen. The idea is then that you tell the machine what it is you want to see, and the machine generates a picture for you. Okay. So in the upper left there, the instruction says this bird is white with some black on its head and wings and has a long orange beak. The first versions of these systems did something like this, right? Not entirely impressive. The upper left is at least a bird, right? It generates this bird out of instructions. And the middle one, I'm not an orth. I mean, I'm not very into birds, but it looks like a bird to me, right? It's quite impressive. So just from these words, the bird is white with some black on its head and wings and has a long orange beak. It generates this. And you know what? These guys, they're not the authors. They never existed. They're computer-generated pictures. There was never people looking like this, ever. That's a little bit of a mindfuck, isn't it? Ooh, I thought I had sound here. There.
Like anyone is saying anything at any point. We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. That's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Thank you. And stay woke, bitches. We're entering an era in which our enemies can make it look like anyone is saying.
It doesn't require a lot of imagination to see how that can cause problems, right? If anyone didn't understand that, that was not Obama saying it, just completely deep. Everything about that was fake, just if anyone missed that. So to go on to something that's a little less intimidating, something like artistic style transfer, which is kind of fun. That's where you're given you have as an input a picture, and they want to see what if Starry Night hadn't been painted out of that window, but what if he would have lived there instead, right? So you mix a certain style with a certain image, and so this painting on the right doesn't really exist. It's completely computer-made from Van Gogh's, inspired by Van Gogh's Starry Night. This doesn't scare anyone, does it? This is just fun AI, isn't it? It's also surprisingly easy to do these things. But perhaps the aspect of AI that captures the public imagination the most is defeating humans at our own games. In '97, the IBM Deep Blue defeated Kasparov, the world chess champion. In 2011, the IBM Watson defeated two of the biggest Jeopardy winners of all times. And in 2008, IBM Project Debater did a pretty good job debating a human. IBM is apparently good at these things. Right? One could argue that Deep Blue won simply by sheer computational force, whereas winning Jeopardy and successfully taking part in the debate requires some kind of understanding of at least natural language. So these victories or these losses kind of hit closer to home, didn't it? Hoppas vinner. Some of these tasks that were previously described, something called reinforcement learning, and that's something that computers do. We do, but computers they're easy to set to work on working on these things. And so I thought I'd show a picture just to get an intuition of how those previous tasks were solved. And this is a Stanford Robot which learns how to walk by, well, much like a baby does, right? By just trying and see what works and what not. So this is its performance. Minute 1. Not entirely impressive. So give it a few more hours of training and a gun, it's kind of scary, isn't it? You just learn this by itself. And what determines how fast something like this the AI can learn is essentially how easy it is to simulate things. I mean, why is self-driving cars a lot harder than playing chess, for example? Well, the world is much more complex and it's a lot harder to get by good data. Whereas to play chess, you can have two computers play 10,000 games against each other in a second, right? So it's a lot easier for the AI to train on things like chess as opposed to self-driving cars. But now we've seen some success stories. It would be remiss to not also show some failures, which can be quite serious and also surprising. These failures are important and natural tasks that we humans do easily, but still pose difficult and open research problems. This is an actual conversation between myself and my Siri. Siri, how old am I? I'm as old as you. Right? How do you know? I know a lot. When was I born? I don't know who you are, but you can tell me. It's not satisfying as a conversation partner, is it? So we still don't have these computers that we can have some natural conversation with. And while training neural networks on huge amounts of data has worked beautifully on image recognition and speech recognition, open domain dialogue still doesn't make sensible results, and they typically fall back on sounding like politicians. And these failures aren't just in extremely hard problems such as robotics and dialogue, they're also in much easier tasks. And this goes back to what I mentioned earlier, that it's obvious that they haven't really understood things. In this field, people are they benchmark themselves. So AlexNet is a neural network which can recognize things with a high probability, right? So AlexNet knows that this is some kind of pyramid. It knows that that's a bird and it's a school bus on the upper left, right? Then you disturb these images only slightly. As those of you who are old enough know what OH-blad is. Right? Yeah. So it's just you have a picture and you put an OH-blad with some disturbances on top of it. From a human being, it's still a school bus there on the upper right and left. Right? The image hasn't really changed at all from our perspective. Whereas the image guesses all these things are ostriches. Which is obviously not satisfying again. Also, some advanced neural networks designed to recognize street signs. This is the same as the adversarial examples in the task before, but here, in this field, you have to disturb the entire image. So after that is, once you know that you can disturb an entire image, it's natural to ask, well, how little disturbance do I need to obtain the same effect? So here, on this highly advanced system for recognizing street signs, if you put those just tags on them, they thought they were speed limit signs, which again shows that it hasn't really understood anything. And this is more dangerous than it sounds, because it could be that if you drive your Tesla and someone puts a sticker on themselves, Tesla will think that there's a curve, even though you're on a straight road, right? So it doesn't require, again, too much imagination to think of situations where this could be not satisfying. Right. More subtle case is the issue of bias. One might naively think that since machine learning algorithms are based on mathematical principles, they are somehow objective, but they are based on data, and data comes from society, and society reflects our prejudice. This left picture was from back in 2015, where Jackie Alkinea, a software engineer, pointed out to Google that, hey, my friends aren't gorillas. Okay. Whereupon Google obviously had to crawl into dust for quite some time. But the thing is, they really didn't solve this problem, because their neural networks are so advanced that to make sure they didn't classify things wrongly again, they just decided that we are not to classify gorillas. Okay, so that's their solution to it. But small failures do little to quench the present hype, right? And governments and companies, they invest massively in this area, and US and China, they're just enormous. And Facebook, Apple, Amazon, Netflix, Baidu, Tencent, all these companies, they have thousands of people working in this area. And while some predict that AI will be as transformative of society as the Industrial Revolution, just as the Industrial Revolution promised to provide a solution to the problem of manual physical labor, AI promises to provide a solution to the problem of mental labor. And just as a history, these optimisms around AI is not new. It started even in the 50s, where John MacArthur and some people at Dartmouth, who actually coined the term AI, they thought that if we just have a summer school with 10, 15 smart people, we'll get there. Obviously, they didn't, but they had some success. Logical theorists, for example, was able to prove some 30 theorems from Newton's Principia. But then they had this AI winter where all funding was shut down. They had some renewed optimism around expert systems in the 80s, which then didn't really pay out either. And when I started my PhD studies in 2002, I kind of wanted to go into AI, but I was told that it's academic suicide. Right? There was just no way to do that. So we've seen this optimism before, but well, we'll see what happens this time. So modern AI tasks are not only change life throughout the plant, they're also appealing and complex from a mathematical perspective. But how am I doing with time?
It's 39. 10 more minutes.
Okay, I'll skip some things then. So to neural networks, which is essentially what made this, everything you heard, all the reasons why this is a hype right now, why people are interested in it, is in these neural networks. Because all the other techniques were just, well, they were there quite a long time ago too, and they're pretty much part of statistics and optimizations research. And this is a query I did on Google on deep learning. Up until 2012, it's pretty much people typing in the wrong words, right? But then it took off. So it was completely dead until 2006, where some first papers were published on it. And neural, why neural? I mean, there's a very clear biological connection to the name, at least. Why do you call it neural networks? And I thought I'd answer that with an illustration. I would now show a picture of an animal, and you'll see it for a very short time and see how long it takes for you guys to see it, see what it is. What was it? Yeah. We're quite fast at these things, aren't we? And that's exactly right. I mean, these systems these AI systems that we train are much like that too. They can do things really fast. They take forever to train and require enormous resources, but once they're trained, they're quite fast. And why is that? Because they don't evaluate various scenarios. If you train a chess computer, in each position has to evaluate a multitude of what ifs. What if I play like this? What if I play like this? What if I play like that? Whereas these things don't feedback on themselves. They just get an input and push it throughout the system, much like we do when we recognize that it's a tiger. We're super fast at it. But that's because we already know what tigers are, right? And what cats are, and what dogs are, and we have a concept of bikes, and other people, and humor, and so why neural networks at all? Why do we even bother? Well, it's very much similar to statistics. That given some data, we want to find a model of the behavior we want to understand. But unlike statistics, which statistics were formed around few data points, right? You'd have your Kramer and Fisher and these giants in the field in the 30s. They'd go to breweries and collect like 200 data points, and from them they did some inference on just what we today know as statistics, right? But as the data sets grow, I mean, regular statistics have trouble managing things that are more complex than just linear, just lines in several dimensions. So in order for a system to do something complex as recognize a tiger or a car or a school bus, you need the underlying model to be rich enough to capture the complex reality. And what's different with machine learning is that you don't explicitly code what it is the machine should do. You just give the neural networks almost infinite possibilities. You say that you can learn anything with this framework, and then you train it to the extent that you train it on data, right? And just from a mathematical perspective, we know that we can approximate any function with just very simple neural networks. You know, the deep in deep learning is that you have a lot of layers. I'll come back to that later. Whereas from a mathematical perspective, all you really need is one hidden layer. You can approximate any function, any type of intelligence with just one layer in principle. But the problem is, so why do the deep, right? Well, it's because that it's a way to save parameters, right? If you were to do a one layer deep neural network and want it to be as as smart as I am or whatever. You require so much data to train on that it would just not be feasible in our universe. Right? But so the main idea, the only reason that people even do deep learning and deep neural networks is to reuse parameters. And I'll give you an intuition around it. To recognize a person, right? What the machine does, it learns different parts, essentially. So to recognize my face, you need to have a pretty good idea what eyes are, and ears are, and noses are, and extremely wide shoulders, what they look like, and stuff like that. And then again, eyes and ears constitute lines and edges and layers. So what you, from an input of pixels, each layer adds an abstraction, much like we do. And we have cells that in themselves have parts that do various things. Cells work together to form tissue or various kinds of muscles. Muscles, various organs coordinate to become us, and we work in various ways to build a society and so on. So the complexity increases for each layer. And whatever, even if you're supposed to, regardless of if you want to recognize an ostrich or a car or me on the top level, they all use lines and edges to see it, right? So at the very core to why we do things in layers is that we to reuse parameters. I don't think I have time for this. So there's obviously a history to this too. The most notable is backpropagation, which, you know, in science people reinvent things all the time. Hinton and Williams and Rubenhart, they've gotten credit for coming up with backpropagation. Yeah, other people say that Newton came up with it like 400 years before, but they still gotten tremendous much of credit for it. But why do these things work today at all? So why all of a sudden do you guys sit here and talk about AI, which you probably thought was on sci-fi back in like just 5 years ago? It turned out that it was all the ideas were there a long time ago. The only difference was really we had GPUs, really, really fast machines to do computations, and essentially enough pictures of cats to train on, right? In '85, there weren't enough pictures of cats. That was the problem with the '90s. And so now images like this one is what how people think of these things. That if you have little data, not so much data, then your traditional statistics works excellent. And if you have more data, then you can go towards small neural networks. And if the more complex the task you want the computer to be able to handle, the larger the network. But larger network, that also requires that you need more data, because otherwise you have the same problem as if you have like 10 data points and want to estimate 100 parameters from statistics. You can estimate. You have very many different solutions that could solve that problem. It's the same kind of issue as if I say Adam, my son, and Joel, one of my other sons, they're together 30 years old. And that's the only information I give you. Then there are a lot of solutions to that problem. And similar things arise here, that if you do large neural networks, it can learn a lot. But for that result to be meaningful, you need to have enough data so that you're actually, it learns meaningful things that are robust to when you present it new data. Just as an intuition around this, is that if you have too small a network, let's say you want to fit something to those data points, the red squares. You try to fit a line that's not complex enough. It doesn't really solve the problem, right? It's not a sufficiently good solution. if you add to the model complexity, like a slightly larger neural networks, you're able to fit the points in a semi-robust way. If you were to add another data point, it's likely that it will be close to this function, right, in the middle. Whereas if you go to the far right, it fits your data set. The more complex model fits the data set exactly. But as soon as you add another data point, it will perform very, very poorly, most likely. So that's the intuition. Is that clear in some sense? No. So intelligence is in some sense, just to clear up, close up, intelligence is in some sense a functions answered in data. And we know from math that we can approximate anything arbitrarily well with just 2 layers. So this whole deep thing we don't really need. So the whole thing, the whole point of deep learning is that people reuse parameters, use some ways to get by with as little data as possible and build the structure as robust as possible. And that should be your main takeaway. Deep learning is the way to reuse parameters, make use with as little data as possible, and data is crucial to these things. That's why chess, we've solved chess, but we haven't solved self-driving cars. Thank you, guys.